Trajectory-based operations, or TBO, is an air traffic management concept that enhances strategic planning of aircraft flows to reduce capacity to demand imbalances in the National Airspace System, or NAS, and provides tools to air traffic management personnel and controllers to help expedite aircraft movement. Through improved strategic planning and management of traffic flows, TBO helps reduce reactive decision-making and use of static restrictions. The aircraft trajectory is the cornerstone of TBO. It is defined in 4 dimensions: latitude, longitude, altitude, and time. Aircraft trajectories are defined prior to departure, continuously updated in response to emerging conditions, and shared between stakeholders and systems as needed. Improved data sharing and information exchange is another cornerstone of TBO. Facilitated by the FAA's Integrated System-Wide Information Management System, or SWIM, collaboration between the FAA and operators is continuous and includes both new and more frequently updated content than was available in legacy systems. Many TBO-enabling capabilities are already available and in regular use, while others are in development and planned for incremental deployment over the next several years. While site-specific operational needs drive the selection of the right tool in the right place, deployments are prioritized on a geographic basis and by considering operational relationships between facilities that manage flows into and out of focal airports. The FAA identified 8 operating areas across the continental United States to reflect these interdependent operational relationships. In prioritizing operating area implementations, the FAA considers trade-offs between benefit opportunities, existing commitments and implementation risks, and readiness for increased use of performance-based navigation, or PBN. This presentation will explain the FAA's rollout strategy in the Northeast Corridor, or NEC, the first operating area selected for TBO deployments. Currently, air traffic management generally moves aircraft along their flight plans as quickly as possible. Limited insight into potential congestion through constraint points in the National Airspace System, or NAS, leads to frequent use of traffic management initiatives, or TMIs, such as ground delays and miles in trail, and may result in either over-restricting or under-restricting of flows. During busy periods at Philadelphia, current ATM practices often lead to more aircraft reaching terminal airspace than the airport can accommodate, and therefore to large necessary delays in the form of vectoring and extended downwinds in the terminal airspace. We call them necessary because they ensure safe merging and sequencing of traffic flows. In 2019, aircraft flew on average 8.8 nautical mile longer distance in Philadelphia TRACON compared to the shortest distance between the same corner post and arrival runway. During periods with high demand, the average necessary delay was almost 17 nautical miles. To improve delivery of aircraft in the Philadelphia TRACON, we are introducing advanced time-based management, or TBM, capabilities that extend look-ahead time horizons and increase accuracy of strategic planning. Philadelphia TRACON is located inside New York Center and is along the boundary between New York and Washington centers. In 2019, about 50% of arrivals originated less than 500 nautical miles from Philadelphia, and 13% of arrivals less than 200 nautical miles. International operations comprised about 10% of Philadelphia arrivals, and unscheduled operations about 31%. The current TBM design supports airborne metering across the white arcs over the Philadelphia's 4 arrival fixes. Each of the arcs is associated with a freeze horizon. When an aircraft approaches one of the freeze horizons, the system estimates its arrival time to the meter arc and runway based on the flight plan routing, aircraft performance characteristics, and wind forecasts. The system sequences this aircraft, determines an available time on the metering schedule, and evaluates any delay that it may need to absorb to meet that time. Once the aircraft crosses the freeze horizon, its place in the sequence and scheduled time of arrival become frozen. We call them frozen because the automation no longer makes adjustments to the aircraft's scheduled time. However, traffic management personnel continue to monitor traffic flows and adjust the sequence of the timing of individual aircraft as needed. The sequence of aircraft through the meter arc also includes aircraft outside the freeze horizon. However, due to uncertainty in airborne winds, possible deviations from expected routing, and other operational causes, their timing remains tentative until they cross the freeze horizon. The goal of improved TBM for Philadelphia arrivals is to enable controllers to manage aircraft further away from the airport, so that delays can be absorbed over longer distances. As a result, the need for vectoring and other maneuvers inside Philadelphia TRACON will be alleviated, and the management of aircraft across all flows will be more consistent and efficient. Improved TBM for Philadelphia arrivals will be accomplished through a phased deployment that gradually increases complexity of required infrastructure and decision support. In the first phase, the FAA will 1. Build a tiered extended metering or XM infrastructure. 2. Enable scheduling of departures from the first-tier facilities into the new infrastructure using XM tools or directly onto the Philadelphia arrival timeline as appropriate. And 3. Enable scheduling of departures from the second-tier facilities into the overhead stream to Philadelphia using the Philadelphia extended metering system. Phase 1 allows us to establish and test our new infrastructure, which encapsulates the whole eastern seaboard and extends over 800 miles from Philadelphia. It delivers tools for managing departure release times by sequencing aircraft through key constraint points on their route to Philadelphia, resulting in departure delays that are more equitable with those absorbed by airborne aircraft and less likely to be disruptively large. In the same time frame, we will also expand the availability of IDAC to additional towers in the Northeast Corridor, which enables electronic coordination of departure release times between tower and center controllers, reduces the need for phone calls between facilities, and provides faster scheduling with decreased likelihood of miscommunication. With the new infrastructure and integrated tools, Phase 1 delivers a foundation for improving aircraft metering of Philadelphia arrivals, the main focus of the next two phases. In the second phase, air traffic controllers in Indianapolis, Atlanta, Jacksonville, Cleveland, and Boston centers will start to actively meter airborne aircraft. They will display schedules and delays, also called times on the glass, for aircraft through the XM arcs shown in burgundy. This expansion of airborne metering will set up the flows as they converge towards Philadelphia and facilitate delivering aircraft in accordance with the metering schedule. It will also alleviate the use of static miles and trail restrictions. In the third phase, airborne metering in Washington will begin. Washington's small size and narrow sectors that deliver arrivals to Philadelphia seriously restrict the ability to absorb any delays. That is why it is critical to extend metering to the adjacent upstream centers before metering inside Washington can be successful. Finally, improved TBM for Philadelphia arrivals will be completed with the activation of airborne metering in New York. Just like Washington, New York has limited ability to absorb delays. Because of the complexity of flows into and out of New York TRACON and the proximity to Philadelphia TRACON, it is critical to extend metering in the adjacent upstream centers before metering inside New York Center can be successful. By improving TBM infrastructure, decision support, and coordination between facilities, management of traffic flows into Philadelphia will be more consistent and effective across the participating facilities. This will lead to a more efficient use of existing airport capacity, along with improved predictability and flight efficiency of arrivals into Philadelphia. Our effort to improve TBM for arrivals into the Northeast Corridor airports does not only focus on Philadelphia, but includes Newark as well. Just like Philadelphia, extended metering design for Newark will expand the range of integrated arrival management and enable participating facilities to manage aircraft based on downstream constraints that may or may not be directly visible to them. The extended metering design for Newark requires integration of additional facilities and will take as much time and effort to develop, test, train, and deploy as the Philadelphia design did. Once we finalize our extended metering design for Newark, we will be able to shift our focus onto improving departure scheduling for arrivals into LaGuardia. The commitments to improve TBM for arrivals to and departures from the Northeast Corridor are formidable challenges that require significant controller participation and training in addition to improvements in adaptation and automation. However, the FAA's rollout strategy for TBM is broader than the Northeast Corridor. Our implementation approach considers the needs of individual operating areas in the NAS. The geographic scope of each operating area is flexible and not necessarily aligned with existing airspace or organizational boundaries. Instead, It is focused on interdependent TBM and PBN operational needs, including readiness to employ new capabilities, as well as the corresponding benefit opportunities and anticipated costs and risks. In addition to the Northeast Corridor, our first operating area, we have started laying foundation for TBM in the Northwest Mountain area and are working on a deployment timeline for the Mid-Atlantic and Southwest operating areas. The FAA plans to introduce TBM capabilities into the terminal domain by deploying terminal sequencing and spacing in the Northwest and Southwest operating areas. We will also bring TBM capabilities onto the airport surface with TFDM deployments at key airports in all of the 4 operating areas and the rest of the NAS. However, TBO is broader than TBM and requires coordination of deployments across programs and controller participation in supplementary training. The FAA plans to deploy TFDM to 89 sites across the NAS, with an additional commitment from the Department of Defense to incorporate this automation platform into their domain. Through integration with TBFM and TFMS, TFDM will expand traffic flow management to the airport surface and improve situational awareness to all stakeholders, including traffic management personnel, air traffic controllers, airports, and aircraft operators. We will continue expanding and improving the existing network of procedures and routing alternatives to enable additional synergies between TBM and PBN. We have already activated use of tower controller pilot data link communication services for departure clearance delivery to equipped flights at 62 towers across the NAS, and are now expanding datacom services to the en route environment to enable routine data communications of frequency changes, altimeter settings, speed changes, and basic airborne reroutes. Together with our stakeholders, we continue improving aviation weather products and data sharing capabilities, processes, and protocols through SWIM. We are collaborating with NASA, MITRE, Lincoln Labs, academia, and other research institutions on future concepts, advanced technologies, and applications. In summary, while TBO capabilities and their implementation timelines may seem distinct, they are intertwined with our sustainment activities, workforce training, and other improvements on our communication, navigation, surveillance, and automation systems. As we continue to transition to the Next Generation Air Transportation System, or NextGen, we are also proactively addressing emerging safety risks and building the foundation for safe integration of new entrants, such as unmanned aircraft systems and commercial space vehicles. In spite of the complexity associated with coordination and management of our initiatives, the FAA remains committed to evolving the NAS through incremental deployments that gradually build on each other and will, over time, successfully deliver end-to-end trajectory-based operations.